Hello physics students. In this video, we're going to learn one of the main ideas in circuits, and that's called Ohm's law. But before we do that, we first have to learn a third idea that goes into Ohm's law. We already know two. One of the ideas is voltage or potential. We've been studying this all year, and there's a couple definitions for voltage or potential. One is that it's the thrust per charge, the joules per coulomb that every single electron receives going through a device like a battery or some kind of electrical device. The other definition is that it's the integration of electric field from one point to another along a path, the amount of electric field that lies along that path integrated. Those two things say the same thing, that basically voltage sources pump charge through a circuit. So you could think of a voltage source as like a pump. And then we learned about current in yesterday's or the last physics video, and that was basically the coulombs per second. I was the charge per time, the coulombs per second that flows through a wire or a light bulb or something. So it's like a flow rate, kind of similar to velocity, how rapidly the charges are flowing through a circuit. Today, we need the third idea, resistance. Okay, so here we are. What is resistance? First of all, we use the symbol capital R. It's measured in ohms. I mentioned this in the last video, and here's the symbol ohms. It's represented by a squiggly line in a diagram. The reason why, as I mentioned yesterday or in the last physics video when I was talking about drift current, when an electron is trying to tunnel through a metal, it's going to hit atoms along the way that sort of deflect it along the way. That causes like delays. It resists the flow of electricity. So even good conductors like copper have resistance. There's a certain amount of restriction to the flow of charge. Now, so almost everything has resistance when there's electricity involved. The exception is superconductors, which are not part of the course, so I'm not going to spend time talking about them. So we can actually calculate the resistance, the ohms of a given conductor. And here's the formula, but basically, first of all, conductors usually are made like long cylinders. But it doesn't matter the shape. If you cut the conductor, the wire, it could be a square wire, and you look at the end, it'll most likely have a circular, or it'll look like a circle, like this right here, right? So there's a circle. So that area, pi r squared of this, is what I'm talking about here. And then, of course, it's got a certain length. All these must be in meters. And then if you plug that data in here with the resistivity, resistivities are found in tables, or you could look them up online. You look up the resistivity of a particular conductor. You plug it, all the data in, you'll get the resistance in ohms. Now this formula shows us some patterns, some concepts. Longer wires have more resistance. So here I have the same aluminum bar, but one is shorter than the other. Has the same cross section if you look at the ends here, but the longer length here means more resistance to this one than this one. And it's to the 1 power, so we see a linear growth, resistance to length. Thicker wires have a bigger area, and so with area in the denominator, they have less resistance. So here I've got two conductors, both aluminum, both approximately the same length. This one has a higher resistance because it's got a smaller area than this one. Okay, so that's also shown in the formula and in this graph. So these are graphical relationships, but also sort of more numerical relationships. Like you need to know that if you double the length of a conductor, you're going to approximately double, or you're going to double the resistance. If you double the area, make it bigger, you're going to have half the resistance. But a reminder that area is not the same pattern as radius. If you double the radius of a conductor, you're actually, because the area is pi r squared, you're you're squaring the factor of 2, you're actually quadrupling the area. So doubling the radius makes 1/4 the resistance. So that's how you could find the resistance of a copper wire with this formula right here. So let me create a pause in case you need a moment to catch up. Okay, so give you some examples. This is a copper wire, pretty skinny. If you look at the cross section, about 1 meter long. I think it's 80 centimeters. If you were to calculate the resistance of this, it would be approximately 0.02 ohms. Small amount of resistance, okay? This aluminum bar, because it's thicker, aluminum's not as good a conductor, but because it's thicker, it has less resistance. If you were to calculate the resistance of this bar, it'd be about 0.0001, about 10 to the minus fourth ohms. Not much resistance to metals, okay? So these are the resistances of wires, but you could also buy resistors. If you go online, resistors for sale, you could buy them. They're pretty cheap to buy. Let me show you some commercially available resistors. So a lot of the resistors you buy will look something like this right here. See this little line? And it's got got a bunch of colors on this little ceramic piece right here. And you could look up online how to read these colors. There's a code to it, and you could figure out the resistance of this resistor just from the colors on it. Now, you could buy resistors like this that are 10 ohms, 1 ohm, 1,000, 1,000,000 ohms, and they'd all look pretty much the same. It's what's inside that makes the resistance. So a lot of resistors look like this, pretty small little ceramic things. Sometimes if they have a pretty small resistance and to allow them to have more current in them, they can be a little bit bigger, okay? So that's a possibility. And sometimes you can buy resistors that are made in ceramic material if there's a lot of current going through. So this is a resistor that I have for a lab in Regents. So this is approximately 10 ohms in this. And because it can heat up so much, it's got all that ceramic material. So you see a couple different kinds of resistors. All right, so now what I'm going to do is do a calculation example, how you could use this formula to calculate the resistance in a wire. So let's move on. We got an example here. We got a copper wire. A certain radius is given. It's coiled around a pipe of 0.01 meters. In other words, the pipe is about 10 centimeters in diameter or radius, and it's coiled around that pipe 100 times, and I want to determine the radius. So it's something similar to this. Basically, we have a plastic pipe here, and someone coiled a bunch of wire. So this is what the problem is saying. We've got a certain radius to this pipe and a certain radius to this wire, and it's wrapped around 100 times. And so we need to find the resistance of this whole arrangement. So the first thing we have to realize is the length of the wire has to be determined from the circumference of the pipe as you're wrapping it around 100 times 2 pi r, which is the circumference of the pipe 100 times. So filling in my data, I see that my wire length is actually over 6 meters long, 6.28 meters long. Once I have the length, I can now go ahead and plug it into this formula that we just learned. And the resistivity, where can I find that? Well, as I already mentioned in the last video, on page 754 of our textbook, there is a table of resistivities, and in it we can see copper right here. And if you go over, you see 1.69 times 10 to minus 8th. The units up here are ohm meters, so I can just look it up and get the resistivity of copper. So that's what I plug in right here. The length, pi r squared for the area. Now this is the radius, the thickness of the wire, or the radius of the wire. Punch it on a calculator and I get about 3.38 ohms. So that's resistance, okay? So if you need a moment, I'll create a pause to allow you to copy this down. Okay, so we have voltage, current, and resistance. Now we're going to put them all together into one idea, one equation called Ohm's law. But to do that, what I want to do is reconfigure the camera because I'm going to show you Ohm's law in action with a circuit so we could see the patterns with an actual circuit. So Give me a moment. So before I show you the workings of Ohm's law through a circuit, I first want to show you some basic important points about circuits and how they operate. So what I have here is a power supply. We used it in the mapping labs already, and a voltmeter. And so I'm going to turn this on, and the nice thing about this is, unlike batteries which work with a chemical reaction, which produce a certain voltage based on the chemicals inside the battery, this can be adjusted to any voltage I want. So what I'm going to do is turn this up to about, you see, I could go 5 volts, I could go 14 volts. I'm going to make about 5 volts on the voltmeter right here. And the other thing I want to point out, an important thing, is that voltage is always 2 prongs. Okay, so I cannot get that voltage by just plugging in one wire into the power supply. You see, now I get 0. You say, well, you plugged into the black one. Plug it into the red one. That's the positive. So, all right, let me plug it into the positive, and I still get no value. Remember, voltage is the joules per coulomb when an electron moves from one point to another, or the electric field integrated from one point to another. But again, that implies 2 points, a starting and an end point. So I need 2 points for voltage. But connection to both sides to get voltage, one is not enough. This is why every cord has at least 2 prongs to it, right? So there's 2 prongs. Cut one of these off, and the appliance will not work. Whatever one you cut off, you plug in just one, it's not going to turn on. Okay, so that's the thing. So now I'm going to take this away, and I'm going to connect this circuit with a light bulb. And again, that idea of 2 prongs necessary. So if I connect this bulb like this to the positive, it doesn't turn on until I complete the circuit. You always need like a circle with current. Different than water, which is why I have the sink here in view. If I turn this faucet on, all that's coming out is like one pipe, and it doesn't need to flow in a loop. The water can squirt out just fine. But if I do that with electricity, the electrons will not squirt out the end through the light bulb. If this worked with a paddle wheel and hoses, I could put the hose like this and have it go like into the lawn, and then the water would go through and turn this paddle wheel, turn the light on in a sense, but not with electricity. You need the loop. Okay, so that's the first point. So now what I want to do is I want to make a circuit that could tell me how voltage affects the current in the circuit. And then I'm going to make another circuit to demonstrate how resistance affects the current in the circuit. So this measured voltage, but how do I measure current here? Well, what I could do is I could take one of these multimeters and I could insert it within the loop. So I'll turn it on, and instead of the electricity returning the power supply, I'm going to plug it in right here and then make it go to the power supply. And what that does is it puts the ammeter within the loop of the circuit. It's like a high-speed toll booth on an interstate. The electrons will register as they pass through this. It doesn't resist the flow. It allows it to pass, and it records how much current I have. So now I've got a measure of the current, about 0.4 amps, as you could see from this meter. And then I want to measure the voltage at the same time. So I'm going to just put this on top here, right on top of these wires, and measure the voltage at the same time. So what I have here is voltage and current. And so what I'm going to do is start down low. And I see that for 0 volts, I have 0 current. But if I put a little bit of volts, let's say 1 volt, about 1 volt, I get 0.23 amps. Let's try 2 volts. More amps. More volts, let's go to 3. And I get more amps. These are going up together. Up to about 5, and I'm up to 0.43. So that's the first pattern we're seeing. More voltage, more current, okay? Now, you could also see that from the brightness of the bulb, right? So this bulb brightness is actually related to the current coming through the bulb. But now what I want to do is see the effect of resistance. So I'm going to reconfigure this circuit because I already learned one idea in Ohm's law, more volts, more current. But now, how can I change the resistance? Well, one ingenious device is this device right here. What it does is it basically creates what we call a variable resistor. If I hook wires here and here, there's very little resistance because the electricity can just go through this post down to this point right here. But if I go like this, the electricity now gets deposited at this contact and has to spiral through all this wire before completing the loop. So by sliding this, I force the electricity to go through more wire or less wire, more resistance, less resistance. So I'm going to insert that into the circuit now. So give me a moment. I guess I don't have the right wires. I guess I could hold it. Yeah, it might hold. And here we go. We see this is very little resistance, and I'm going to add more resistance, and you see the bulb brightness goes down. So more resistance, we would have seen less current if I had the ammeter there. We see that through the bulb brightness. More resistance, less current, more voltage, more current. So now we're going to put those together into an equation called Ohm's law. So here it is, the equation that summarizes the patterns we just saw. But you know what? I didn't even have to show you the circuits earlier, because if at the start of this year, before you had even studied any of the topics that we covered over the course of the months, I had asked you, you have to answer this question, you have to guess. If you crank up the voltage on a circuit, is that going to make more or less current in the circuit? Most people would probably say, you know, more volts, probably going to be more current. And it would be correct. Basically, in other words, that would just be kind of like common sense. And the same thing for resistance. If I were to say, okay, I've got an electrical circuit and somehow I make more resistance in it, does that make more or less current in the circuit? Most people would probably say, more resistance, probably less current. And you would be correct. So this equation is very much common sense. It's very nice. More volts, more current, more resistance, less current. The patterns shown graphically look like this. As the resistance goes up, you have like a 1 over x graph. Notice though, as resistance goes to 0, the current spikes up. Okay, so that's something important to know in circuits when you're actually designing circuits. You don't want that to happen. It could cause fires and such. The voltage relationship, you see a linear pattern, you see current voltage, you see a nice straight line. But then, some of you who were paying attention may have noticed something when I was showing you the circuit with the light bulb. When I doubled the voltage, I did not get double the current. And same thing when I tripled. And the reason for that is because the light bulb, the way it works is it gets hot. It glows because it's hot. And when resistors heat up, the resistivity, those numbers, those constants I looked up in the textbook, they change. Something that's not in the formula we learned is the temperature dependence. The hotter the resistor, the more resistance it has. And so for a lot of situations, the resistor doesn't heat up because it's able to dissipate the heat that the electricity creates in it. But if you crank the current too high, it starts to get so hot that it can't cool off fast enough, and then the resistance starts increasing, and you would see not the same amount of current you would expect, but less because there's more resistance suddenly because of the heat. So when there's a linear pattern, that's referred to as ohmic or ideal behavior to the one power, because it follows Ohm's law. But in real life, when things get hot enough, there's enough current, then things start to display non-ohmic or non-ideal behavior. But most of the time, we're going to stick with this situation where we're within Ohm's law in this topic, in this course. So if you haven't already copied that down, I'm going to create a pause to allow you to copy it down. Okay, so one other thing that we have to do today, it's part of the curriculum, being able to derive this formula for the resistance of a wire, okay? And it turns out that Ohm's law is how you do it. So we've got a battery, we're going to connect it to this resistor, this wire here, and we're going to assume that the resistance of all these wires is negligible. It's so small we could practically say it's zero. We're also going to assume that there's no resistance inside the battery. Not true, it's made of metal. So we'll learn about that later in the course in this topic. So one thing we could begin with is the definition of current density. It's current over area. Maybe I'll write that out here so you remember that it's not amps. Current over area. And then another expression we learned in the video yesterday, or the last video, was that that is caused by electric field. 1 over resistivity times electric field is the current density. So we begin there. But what we could do is we could replace the electric field with voltage from the basic formula that V equals ED. There's an electric field that goes like this and this from plus to minus. And so the voltage across here is the voltage there. E times the length of the wire. So if I solve for E, it's V over D or V over L. Okay, so see the color there coordinated to help you out. So I'm almost done here. I just have to do a little bit of algebra. So what I'm going to do is I'm going to divide I over to this side, and then I'm going to move the rho L to the other side. Okay, so divide the I over there, and then the rho L to this side gives us rho L over A on this side, and V over I. Now remember, I was equal to V over R. So if I move the R to this side and the I to this side, I have R equals V over I. This is R. So I could replace all of this with R from Ohm's law, and there is my final expression. Okay, so again, part of the curriculum, you need to be able to derive that. All right, so if you need a moment to catch up, I'll create a pause to allow you to copy this down. So that's it for today. We learned how to calculate the resistance of wires with this expression, and then that completed the 3 ideas, the 3 basic ingredients in Ohm's law: voltage, current, that was yesterday, and resistance. And they all go together in this very simple, very common sense expression. I equals V over R. More volts, more current, more R, less current. Common sense. All right, so the homework tonight will just be applying these formulas, all algebra-based. You shouldn't have any problems. I hope you don't have any problems. I hope you enjoyed the video. I hope you enjoyed the idea of Ohm's law and also the basics of how circuits work. I'll see you in the next physics video.